Now we do a very important lemma. It's called the Satz von Atkinson's theorem, and it goes like this. So let X be a Banach space and T be a continuous operator. Now the following statements are equivalent. Now what are these statements? So T is Fredholm. It's equivalent to that there is an operator S belonging to the space of continuous functions such that image of I minus st and image of I minus ts are finite dimensional. If this holds, then T is Fredholm. And if T is Fredholm, then this holds. Similarly, if now the third one is there is an operator belonging to the space of continuous functions from x to x such that I minus st and I minus ts are compact, then I can say that T is Fredholm. So, and the fourth one is there are operators S1 and S2 belonging to the space of continuous functions such that I minus S1t and I minus ts2 are compact. Then I can say that T is Fredholm and vice versa. Now the reason I am going so much in detail with this four statements is that we would extensively use them in the time to come. We have a range of theorems that it's absolutely essential to know these things by heart. So let's look at some other things. So now I can say that, okay, now let's prove other things. So let's look at this. Now I say that lambda I minus t, where lambda is not 0 and t belong to the space of compact functions, is Fredholm with index 0. Now if I can prove that, so now I had like let x be a Banach space and t be a compact, then lambda I minus t is Fredholm with index 0. That's what I had. Yeah, similarly here also I had a theorem that let x be a Banach space and t be a compact operator, then lambda I minus t is Fredholm. The operator S in statement 3 is itself Fredholm since 3 is symmetric in S and T. So what was 3? Let's write 3 again. 3 says that there exists S belonging to Lx such that I minus ts and I minus st are compact. Now initially I knew that T belonging to Lx and X was given to be a Banach space in my proposition, if I remember correctly. Yeah, so X was a Banach space and T was Lx. So, and X was Banach space. And then I say that, okay, that say T is Fredholm is equivalent to this. The operator S in statement 3 is itself Fredholm. So this it's Fredholm because it's symmetric in S and T. So if looking at this statement, I can say that, okay, since there exists S in Lx such that I minus ts and I minus st are compact, so I say that, okay, T is Fredholm. If I believe this, I can say that, okay, if I minus ts and I minus st are compact, then I can say that T is Fredholm. But I can also say that if I minus ts and I minus st are compact and T is also belonging to Lx, then I can say that S is also Fredholm. Can you see the argument of symmetry here? So let's convince ourselves of that. So if you just look at these equations, you should be able to see that because of the symmetry argument, S itself is Fredholm. Now if statement 4 holds, what was statement 4? Statement 4 was there exists S1 and S2. So fourth says that there exists x1 and x2 belonging to Lx such that I minus S1t and I minus t S2 are compact. So now if I see, let's do S2 minus S1. So S2 minus S1 can be written like this. Now if you see from above, I know that if 4 holds, now this one is saying if this one holds, now if 4 holds that S1 and S2 belong to Lx such that these are compact, then I can say that okay, T is Fredholm. But now what I can do is I can check S2 minus S1, and it comes out that this is also compact, because see, this is compact given and S2 is bounded. Similarly S1 is bounded and it's compact, so it becomes a compact minus compact, so it's compact. And now I can see that okay, indeed, if I just do trickery and I rewrite the equation, then I can see that this is compact. It was given, and I found out that this is compact and this is bounded, so this quantity together is compact. Similar argument in this case, so I can say that S1 and S2 are also Fredholm, because if you remember from before, there was this 3 and it told me that there exists X belong to Lx such that M I minus Ts and M I minus St are compact. And if you see in this case, so 4 gave me that I, so if I see from 3, I know that there exists L belonging to Lx such that I minus Ts and I minus St are compact. Then I saw that and I say that okay, then T is Fredholm. I told that. But now I get that this I got from 4 above, that I minus Ts1 is compact, and now I prove that I minus Ts1 is compact. Before I knew that I minus S1T is compact, so I can say that indeed S1 is also Fredholm. The similar argument follows, and S2 is also Fredholm. And the next thing that I would like to discuss is the lemma. Now let X be a Banach space and A, B belong to Lx be Fredholm operators. It follows that AB itself is Fredholm with index of AB as index of A plus index of B. Now according to Atkinson's theorem, there exist SA and SB belonging to Lx such that I minus SAA, I minus ASA, I minus SBB, I minus BSB are compact. Why? Well, it's given that A is Fredholm, which means that this and this must be compact. Atkinson's theorem tell me that, and similar argument for B also. And now I say that okay, now I just rearrange the equation. So I can write this equation here, that I minus AB SB SA as this. So I knew that this is compact given A is bounded, SA is bounded, so this becomes compact. A similar argument here also. So that I now prove that I minus AB SB SA is compact, and I say that this is compact. Now I know that SBSA. So what did I do? I said that in order to prove that AB is Fredholm, I had to prove that there exists S belonging to Lx such that I minus SAB and I minus, let's call it S tilde, I minus AB S tilde are compact. So if this is the case and AB belonging to the space of bounded function and X is a Banach space, then I can say that okay, AB is Fredholm. But that's the same case that happened here. So I say that okay, this is compact because this quantity is compact. So indeed that S tilde in our case is SBSA, and I can say that again, okay, AB is Fredholm. So now this tells me an important thing, that if I have two Fredholm operators A and B, then AB is Fredholm. And similarly the indices of AB is indices of A plus index of B. Now the next thing that I see is that let X be a Banach space. So the next thing that I would like to talk about is this corollary. So it says that let X be a Banach space, T be a bounded operator or be a Fredholm operator, and S be an operator such that I minus ST and I minus T are compact. So both S and T are Fredholm. And now it follows that the index of S is minus the index of T. Now it is because if I minus ST and I minus TS are compact, so I write K as I minus ST, And so st is equals to I minus k. Now I minus compact is a Fredholm operator with index 0, and I saw in the previous theorem above that index of AB is equals to index of A plus index of B. So index of st, so st is Fredholm with index 0, so index of st is index of s plus index of t, and thus index of s equals to minus of index of t. Now a very important theorem that we would see is this. We say that X is a Banach space, T be a Fredholm operator, and K be a compact operator. It follows that T plus K is Fredholm with index of T plus K is equals to index of T. Now what I mean is that compact perturbations of Fredholm operators are themselves Fredholm with the same index. That's all it means. And the way we prove it is where we make use of Atkinson's theorem again. We say that let S be a bounded function such that k1 equals to I minus st, k2 equals to I minus ts are compact. Now it follows that if you look at this, I just did one thing. I just wrote these two equations as they are. So k1 is I minus st and minus sk I just added. I just wrote these equations. Now if you look at this equation, this is compact, this is bounded, and I know that k is compact. And similarly k2 is compact, s is bounded, and k is compact. So this itself is compact. So I minus st plus k, I minus t plus k s is compact and s is bounded. So I can say that t plus k is Fredholm, and the index of t plus k, now if you see that, is equals to the minus index of s, same because of this, same because of the corollary that we did above, that the minus, that I minus st, I minus ts are both compact, so index of s equals to minus of index of t, so index of t plus k equals to minus of index of s, but this was equal to the index of t, and that's pretty much it for this corollary. So now we have this lemma. It says that let X be a Banach space and T belong to continuous functions. Now the following statements are equivalent. So T is Fredholm with index 0 is same as saying that T is the sum of an invertible operator and an operator with finite dimensional image. It is equivalent to saying that T is the sum of an invertible operator and a compact operator. Now of course this T, the index of T is 0 all the time because one implies the other. Now we saw before that if T is a sequence of operators with finite dimensional image and Tn converges to T, then T is compact. Now this was true in the case of Banach spaces. Now in Hilbert spaces, this condition changes to if and only if. So T is compact if and only if it is the limit of a sequence of operators with finite dimensional range. Now the next thing that I would like to talk about is this fact here that all operators with finite dimensional image are compact, but not all compact operators have finite dimensional image. And this is pretty much it for the lemma. The next thing in this section that I would like to discuss is, so now let X be a Banach space and the set fx of Fredholm operators on X is an open subset of Lx. So it has written that it's an open subset of Lx. Now moreover, the index is locally constant on f of x. Now this is the set of Fredholm operators, and he's saying that the index is locally constant on this. What this means is, so this is f of x, okay, and as a sequence of operators, so this is a sequence of operators Tn converging to T, and I know that for every operator T I can find a radius on epsilon of a ball of radius epsilon such that the index is constant here. But if you see carefully, this index is a mapping from fx to z, so the z is an integer. So now look at it this way. So I have the space and there is a sequence Tn which converges to T, And I know that for this t, as I have seen before, that the Fredholm index remains constant. So if you see that what we did before was that the compact perturbations of Fredholm operators are Fredholm with the same index. So now I can say that, okay, I can find, so within this ball, the Fredholm index remains the same. So as soon as my Tn reaches this ball, the index of Tn and is constant in this complete region. So what's happening is as Tn reaches to T, so continuous means that as Tn tends to T, index of Tn should tend to index of T. But as soon as Tn tends to T, as soon as Tn enters this ball, this index is constant. So that's what I've written here, that as soon as the sequence enters this ball, the index remains constant. So the index is a continuous function, because continuous means that as Tn tends to T, index of Tn tends to index of T. But as we see that it is pretty much constant, so it is of course tending to it, because 2 tends to 2, that kind of stuff. So now a continuous function is all integer valued. So this continuous function here is an integer valued, and I know that all integer valued continuous functions are constant. How do I know that? Because if you see that if the value, so if the function is continuous, it means that if Tn tends to T, then f of Tn tends to f of T. But if this integer valued, meaning this is an integer, then the only possible way for this function to be continuous is that it is a constant function. So yeah, that's pretty much it for this lemma. So I know that the index of Fredholm operators is constant over connected components. So the index must be constant on all connected components of f of x.